So far you've been exhaustively testing, doing an exhaustive test of a combinational logic circuit. And remember how you set stuck-at faults around each gate, and then if there were two on the same wire that were the same, then you could cross one out, et cetera, and you got down to a smaller set of test inputs to exhaustively test your circuit. This time, but there's other times where there might be a really important node, and if that node is correct, then probably your circuit will work okay. So let's see how you would check this big circuit right here for a stuck-at-0 fault here. So if you're checking for a stuck-at-0 fault, the first thing you know is you need a 1 on this wire. Okay. And if it's wrong, it will be a 0. And remember, with circuits, if you have them in a chip, all you can do is set inputs and watch outputs. So this 1, if it's wrong, if it's actually a 0, where you set this wire to 1, but it actually ends up showing up as a 0, that has to somehow propagate through this AND gate or propagate through this OR gate and out to out 2. So you can say, hey, oh, that node is not behaving correctly or is behaving correctly. Now, I forget which animation comes up. Oh, yes. So there's no path from this node to out 1, so we don't care about that. And if we don't care about out 1, then we really don't care what's on that wire. And we don't care about what's on that wire. So, and this is a weird OR gate. I guess I needed another input there. But we do, if we're going to use the AND gate to pass the result of this wire through, then we need a 1 on this side of the AND gate. And that will give us a 1 if it's working correctly, and it'll give a 0 if it's working incorrectly. Okay. To get a 1 here, you can have a 1 on any one of these inputs, or all 3, or just 2, but somehow you need to make this OR gate give you a 1. Okay. So we've figured out how to get this signal out to this wire. If this signal is wrong, it's going to be a 0. If it's right, it's going to be a 1. When we want to pass that through, and to pass that through, then you need a 1 on both of these other wires. Otherwise, if there was a 0 on either one of these wires, it wouldn't matter what this value was. It would always be 0 on the output. So to make this set as a 1, if this is a 0, it goes for the inverter and makes it a 1. But if you, and that's good, because if you get a 1, then you get a 1 here. If you get a 1 on this node, which is the correct answer, you'll get a 1 here. If you get a 0, in other words, this is actually stuck at 0, you'll get a 0 on this wire, and you'll get 0 out for out 2. So that works well. 0 puts a 1 on there and makes that a 1. And then really you don't care what that is. If one of the inputs is to this OR gate is already 1, you're going to get a 1 there. But you need to put a 0 on this line. So any one of these inputs needs to be a 0. And then this wire, if you're passing this value through, that also needs to be a 1. This wire needs to be a 1, which means both inputs of this AND gate have to be a 1. So you need to have this 0 from this AND gate in order to get the 1 here. So that's good. That's already taken care of. But this side already has to be a 1. And to do that, one of the two inputs have to be a 1. Now this becomes a 1. And if this is working correctly, out 2 will be a 1. If it's working incorrectly, then out 2 will be a 0. And so in this way, now we have a test vector. As long as one of these wires is 1, we don't care what the value, whether it's 1 or 0 on here. As long as one of these wires, at least one of these wires is 0, And as long as one of these wires is 1, we should get a 1 on the output, but if we get a 0, we know we have a stuck at 0 fault.